Welcome to the demonstration of the Bleichenbacher attack. So here we are going to demonstrate the Bleichenbacher attack. First we study the mathematics behind the attack and then get on with writing a Python code which will in fact simulate the attack. So let's get started. So first what we need to know is that the RSA is compliant with the multiplicative property. So basically this expression remains true. E of m into E of s mod n gives E of ms mod n. So this is important during the attack. We'll get on to where this is used. So Bleichenbacher describes this attack based on the padding of an encrypted message in RSA. So this is a side channel attack which tries to get some information about the message which is encrypted using the information from an oracle which will say whether a padding of an encrypted message is going to be right or not. So here we are going to specifically deal with PKCS number 1 version 1.5, and the padding scheme is as follows, and it is shown over here. The first 2 bytes will be 00 and 02, which is in hexadecimal, so that will be in 16 bits in total, then followed by a random padded numbers, then followed by 2 zeros, then our message. So basically this whole thing will come up to n, which is the key size, which will take us 1024 in our particular example, and based on this padding scheme we'll write an oracle which will in fact check whether the message is conforming to the standard. Now suppose if a encrypted message is of this padding format, then it should lie basically between 2b and 3b minus 1, where b is 2 raised to k minus 16. So 2 raised to k minus 16, where k is the number of bits in our n, which is 1024. So this will look like this: 001 followed by a lot of zeros. So if we multiply it by 2, it will be starting at 0002 followed by a lot of zeros and ending just before 0003. So all the numbers in between will actually be conforming to the padding standard of PKCS number 1 version 1.5. and so we use this particular set of values to determine some information about our message. So suppose our message is correctly padded, then we know that it lies in between these two intervals, 2b and 3b minus 1. Now using the multiplicative property of RSA, we determine another message m1, which is equal to m0 into s1 mod n, where s is a number we check randomly until we get something that is of the correct format of our padding, so which is m1. So suppose we find an m1, then it will lie between 2b and 3b minus 1, as we discussed before. And from the definition of modulus, we have m1 is equal to m0 into s1 minus rn. So r is a random number that we don't know right now, and n is our mod n, so n comes from there. So now we basically know that m1 lies in between these two intervals, 2b and 3b minus 1. So using a and 1, we can write we can find out that m0 lies in between 2b plus rn by s1 and 3b minus 1 plus rn by s1. So we basically substitute the values, the lower and upper bounds of m1 in this particular equation number 2, and we get the interval in which m0 lies. So basically what we found out was, we knew initially that m0 lies between 2b and 3b minus 1, but we basically reduced it by finding another m1 using an s1. So in this limits we have a random number n, which it's not actually random that we find out, so we do not know it now, so we need to find it. So we know this equation where m1 is equal to m0 into s1 minus rn. So we find an equation for r from there, and we substitute these limits for m0 and m1 to find out the limits where R lies. So here we have m0 into s1 minus m1 by n. So m0's lower limit will be 2b plus rn by s1, and m1's upper limit should be taken since it is subtracted. So m1's upper limit will be 3b minus 1, and when we substitute it, we will get the lower limit of r, which is 2b into s1 minus 3b plus 1 by n. And similarly, when we substitute the upper limit of m0 and lower limit of m1, we can get the upper bound for r, and as you can see over here, it's 3b minus 1 into s1 minus 2b by n. So we basically find out the limits in which we have to check for r if we know a particular value for s1. Now let's see how to use this. So before that, we know that the upper limit of r is of this form, 3b minus 1 into s1 minus 2b by n, so which is clearly less than 3b into s1 by n. So if we have an s1 where n by it is equal to n by 3b, then if we substitute it, we can get that r is less than 1. So this in fact means that r will be 0. Since r is a integer, so if it is less than 1, it should be 0. So this is not really helpful for us, because we will get m1 is equal to m0 into s1 from our equation number a, and this clearly means that m1 cannot be correctly padded. This is because we have the smallest value of s1 equal to 2, and for that, and the smallest value of m0 will be 2b from our initial limit. So 2 into 2b will be 4b. So it is clearly out of our bounds, because we need a number between 2b and 3b minus 1. So this is not really helpful if the value of s1 is less than n by 3b. So what this means is that we only need to check for s1 starting from n by 3b. So we start from n by 3b, and using a ceiling function, we'll check the first integer from that particular point, and then we increase it by 1 until we get a correctly padded message. So I'm just going to summarize what we discussed so far. We find an s1 then which satisfies this particular equation where m0 into s1 mod n is equal to m1, and m1 satisfy our particular padding scheme. So then we find various possibilities of r using the equation over here, which is b, and then we find intervals of mo using the various integer values of r using the equation number 3. So we are trying to reduce the interval sizes for our m0, and we are trying to find a single value of m0 which is going to be our final answer. So that is how we crack this particular problem. So now we basically repeat this process. When we find various values of s1 and we get the different values of r, we basically get a lot of smaller intervals in between what we initially thought. So we basically repeat this process in each of these intervals until we get only a single possible value. So that is going to be our final answer. And this basically means that if it's a general interval a comma b, then our equations that we found out before, it will change to these two. So you can see over here, we will use this equation in our Python code. And one more thing we can optimize is that if there is only a single interval obtained for a mo, that means when we find an s1 and we find that there is only a single integer r corresponding to that s, then we basically will have only one interval for m0. So if we have such a case, then we know that m0 clearly lies between a single interval a comma b, and we can substitute that over here if for the limits of s1, and this is what we get: 2b plus rn by b less than or equal to s1 less than or equal to 3b minus 1 plus rn by a. We basically substituted the values of m0 in the equation that we found out earlier, and we got that. So what's really helpful in this equation is that when we substitute a value for r which is greater than 2 into b times si minus 1 minus 2b by m, we get this particular equation for the lower limit of sy. So if we substitute that, we clearly say, if you work it out, you can find out that it is the value of si is less than 2 times si minus 1. So if we have a value of s1 which si which is large, it basically means that the interval size for the particular m0 is going to be small. So in each interval for m0 has a size of b by si. So if we have a larger si, then the interval that we find out for our mo is going to be small. So if it so from this equation we found out that the interval is going to be twice as large. So we basically narrowed it down to one of the halves. So it's going to be like a binary search. So this is an optimization that we can bring in our code by substituting the value of r as 2 into b as I minus 1 minus 2b by n if we have only a single interval for m0. So we'll do that, and this is going to bring this is going to make it fast. Now let's move on with the code part. So now, okay, so this is the Python code where we have a ceiling and a floor function that basically rounds off the fraction into the upper integer over here and a lower integer in case of floor. Then we have written an oracle which is based on the padding scheme we have here, PKCS number 1 version 1.5. So, and this is initially we check whether our message, our number contains 0002, which is the first first 2 bytes for our message. Then we check whether the 00 is present, which should be there after the random set of integers, and it should not lie between 4 and 19, because we know that for our padding the random number of random numbers should be 8 bytes. So since a byte is going to be 2 characters in hexadecimal, we are going to have these many. We have to check whether that 00 is not present there, and basically if this is confirmed, then we have a number which satisfies our padding scheme. Now this is a modulus that we obtain for RSA over here. Let me just show you how to find that. Now, okay, I have initially created a key of 24 size, 1024 size, and this is the modulus that we obtained over there, and this is what I have copied it into our code. Now we find the n by converting this modulus into an integer, then find k as a number of bits that n takes by finding the log of that to the base 2. Then we find our b. Then we have our padded message over here, which is starting with 3 zeros and a 2, followed by a random set of numbers, then, which is in hexadecimal, and somewhere over here we should have a 00 like right here. So all these are random padding, and after that that's our message. So this is what we are going to find out from our attack. So at the end we are going to check whether this particular set of characters is going to is in fact our message itself. So we are going to check that. So as we discussed in the mathematics, this we are going to just substitute those values over here into the limits, and we basically find the various intervals of m0 by using the exact fractions that we discussed before. Then this is our simple code. You take this code into consideration if we only have one a single interval for our M0, and we are going to get the value of R as this, as we discussed before, and we change the limits of Si to this one, which is in fact lesser than the previous one, and this is our optimization over here. And if our number of intervals is going to be greater than 1, then we are going to be, check each of those values of intervals, and we substitute for Si using our initial set of range, and we basically find all the intervals that comply with the which lies in between 2b and 3b, so which is over here, and just like that we find all the intervals for M0. And if we only have a single interval and it is the same, then we have basically found out the message that we are looking for. So we are going to print it, and we are just going to print the number of iterations where it happens. So basically, just let's go and run the code and see what happens. And oh, looks like I made a mistake. Okay, so now I have successfully run the code, and you can see over here the value of R is 4, and it has completed the search in 989 iterations, and this is basically our message that we were looking for. So let's see if the particular value after 00 is in fact the message that we were trying to find. Let me just convert this hexadecimal into ASCII and see. Okay, so okay, this ran successfully, and we have now completed the Bleichenbacher attack using the padding scheme PKCS number 1 version 1.5. So that's it. Thank you for listening. Bye.